Yeah, so this will be a tag team between Craig and I. I'm going to try to keep this part as short as I can. I guess before we get started, Andy just asked me to make an announcement. So for the mathematician in the audience, if you are planning to submit a proposal to SATC, there was a suggestion maybe try to team up with one of the cryptographers in the audience. So I'd be happy to help. Craig, Chris, David, I'm sure we'll all be, Mariana, we'll all be interested in helping out. So let us know if you want to apply. Andy, did I say that fairly enough? Right. All right, so let's see. So I'm going to go through this as quickly as I can. This is basically a failed attempt. So this didn't quite work, but I thought I'd tell you what this is about and see maybe you can make it work or tell me that it's never going to work. All right, so we'll do this quickly, and then Craig is going to talk about FHE, and then we'll swap again. So starting first of all with a kind of a philosophical message. So if you think about what the cryptographer's job is, what is cryptography about really? It's essentially about, we sit around and design these complicated systems. The systems themselves are designed to work in this very interactive environment. Yeah, and I'll give an example in just a minute. So there's like a complicated environment that the systems work in, but instead of arguing about security in this complicated environment, kind of the job of the cryptographer is to give a security proof to basically reduce security from this environment to a very simple complexity assumption, so that if the assumption holds, then the system is in fact secure in this complicated environment. Yeah, so you go from a complicated interactive game into a non-interactive complexity assumption. Now we don't have to worry about the complicated game. All we have to do is just analyze whether this assumption is correct or not. And if it's correct, if the assumption is correct, we know the scheme is secure in the complicated settings. And just so that I'm not too abstract, let me give you one trivial example. Like if we have a digital signature system, we talked about signatures yesterday, right? So we have a key generation algorithm, we have a signing algorithm that signs messages, and we have a verification algorithm that verifies signatures. Signatures generally, again, they work in kind of in this interactive environment. This is kind of the standard security game for a signature scheme, where the challenger gives the adversary a public key. The adversary can ask for signatures on all sorts of messages of its choice. And then it's finally, and it does this many, many, many times. So it gets to see the signature on whatever message it wants. And finally, it's supposed to produce some new message signature pair, namely some pair that it has not seen before. So this is this kind of, as I said, it's kind of this interactive environment. And what we need to do, what the cryptographer's job is, design signature schemes that are secure only if you don't have to worry about this game. The signature scheme will be secure in this game if this assumption holds. So reduce interactive settings to non-interactive settings. This is kind of what all cryptography is about. So RSA signatures are an example of this. Sometimes we have to cheat with these things called random oracles, which I won't get into here. But basically, with RSA signatures, you're guaranteed that as long as it's hard to take Q to one end, this particular signature scheme should be secure in this interactive environment. And this has served us really well in lots and lots of different settings. So when we talk about public key encryption, signature key exchange, in fact, the systems that are used on this laptop today essentially go through this provable paradigm where, again, the systems are designed for the interactive game, but security is based on a non-interactive assumption. Yeah, so from an interactive game to a non-interactive assumption. However, there's one area of crypto that's absolutely crucial where we have been completely unsuccessful. Yeah, so here, the best systems that we have are actually systems that are designed using this provability point of view. Yeah, reduce an interactive game to a non-interactive assumption. When it comes to these things called secure pseudo-random functions, which I'll define in just a minute, we have failed completely. Yeah, and in fact, what's being used today has no non-interactive assumption underlying it. So let me explain what are these pseudo-random functions, and now I'll give you just a hint as to why they're so important. So I'll define what pseudo-random functions are in two steps. Yeah, so first I'll define them as what's syntactically what they are, and then I'll explain what does it mean for a pseudo-random function to be secure. So syntactically, what's a pseudo-random function? Well, it's really easy to explain. It's basically a function that's efficiently computable. It takes two inputs, a key and some value, and produces another value. That's it. That's a pseudo-random function. Efficiently computable function that takes these two inputs. The question is, what is a secure pseudo-random function? So if you haven't seen this before, the definition of security might seem a little strange, but believe me, this is the correct definition, and that this is what we need to do to make it useful. And so let me walk through this definition, and my goal would be to actually construct these things. Okay, so what is a secure pseudo-random function? So again, it's defined by an interactive game. Okay, so it's one of these complicated interactive things that we've seen before, and it's actually defined using using actually two experiments, but the two experiments are very similar. So let me explain what the two experiments are. So in the first experiment, what we do is we choose a random key, and we allow the adversary to evaluate the function at any point of his choice, right? So he chooses an x in the domain, in x, in capital X, and then it gets to see the corresponding value, and the attacker can do this again and again and again and again, as many times as it wants. So it gets to see the function at as many points as it wants, and then it outputs some bit, which we'll denote by B0, because in experiment 0, we'll say it outputs B0. And then we do the same thing, except now, instead of evaluating the function f at a random key, you notice here the attacker doesn't know what the key is. The key is secret. He just gets to evaluate the function at a bunch of points without knowing what the key is. In this game, we're going to choose a truly random function from the set x to y, so a truly random function, and we allow the adversary to evaluate this truly random function at as many points as it wants, and again, eventually, it outputs some bits. Now, we say, so in one case, it's interacting with a pseudo-random function at a random key. In the other case, it's interacting with a truly random function. And we say that the pseudo-random function is secure if basically the adversary, if no efficient adversary can distinguish between these two games. And I'm going to be fuzzy about what is efficient and negligible here. Let's not worry about that. Basically, we're saying that the function is secure if essentially the probability that it outputs 1 in experiment 0 is the same as the probability that it outputs 1 in experiment 1. In other words, the adversary behaves the same whether it's interacting with this challenger or whether it's interacting with this challenger. And another way to say it is, it can't distinguish the pseudo-random function from a truly random function. All right, so for all practical purposes, if you choose a random key and you let the adversary evaluate the pseudo-random function, that's the same as letting the adversary interact with a truly random function. This is a very, very powerful object. It should seem impossible to you if the key space is very small, right? The number of functions from x to y could be astronomical if x and y are sufficiently big. There's lots of functions from x to y. Potentially, the number of keys is not that big, and yet still the adversary can't distinguish this pseudo-random function from a truly random function. So these things are, we believe that we can actually build these things. Obviously, we don't know that they exist. It could be that p equals np, and all sorts of things go bad. But we believe that we can construct these things. I guess before we talk about constructions, let me just show you why these are such important objects. So they're kind of the workhorse of all of symmetric crypto. So you can do encryption, data integrity, key derivation, user identification with them. They're really used everywhere. They're really, really quite fundamental objects. And so just to show you how you would use a pseudo-random function, let me give you one example in terms of an identification protocol. So here Alice wants to go through this door. It's really fortunate that we have an Alice in the room. Yeah, so there's no Bob, is there? Not here, good. Right, so anyhow, Alice wants to open this door, get this door to open. So the door says, well, prove to me that you're allowed to open the door. So Alice and the door will have a shared key, and Alice walks up to the door and says, I want to prove to you that I know the secret key. So the way you design an identification protocol, here's one example protocol. And the way it works is the door sends Alice a random challenge. Alice is going to respond with the pseudo-random function evaluated at the random challenge. And the door opens if, in fact, Alice responded with the correct value of the pseudo-random function. Now, why is this a good protocol? Why is this a good identification protocol? Well, you can imagine an adversary that actually, I'll just say here, this protocol is secure against what we call active adversaries. So you can imagine an adversary that gets to interact with Alice. So he pretends to be a bad door and gets Alice to interact with him. And so then he gets to learn the value of the function in lots and lots of different challenges. So he gets to supply Alice with all sorts of challenges of his choice. And for each challenge, Alice will give the adversary the value of the function at that challenge. So the adversary gets to see the value of the function at many points of his choice. Then Alice walks away. The adversary is supposed to turn around and be able to open the door. But if the function is a pseudo-random function, when the adversary talks to the door now, the door will give the adversary some new random challenge, which the adversary has probably never seen before because the challenge space is supposedly sufficiently big. Yes? So the adversary has never seen before, but because the function is pseudo-random, it's a secure pseudo-random function, it behaves like a random function. The fact that you've seen it at many values of your choice doesn't help you determine it at a value that you have not seen before. This is true for a truly random function, and therefore it must also be true for a pseudo-random function. And that's why this protocol is secure. Even against adversaries, they get to interrogate Alice and get her to answer queries before the attacker does his attack. Does that make sense? So this kind of shows you how we use the pseudo-randomness property. Make sense? Yes, Hendrik? Everybody's happy? Okay, excellent. Excellent. So that's a secure pseudo-random function. All right. So how do we construct pseudo-random functions? Now that we understand this is kind of a really important concept. How do we construct them? Well, this is kind of the bad news. There's only one pseudo-random function, well, mostly one pseudo-random function that's used in practice, and that's called the AES function. So AES is this complicated circuit. You see it has a key space. It takes 128 bits as input, outputs 128 bits as outputs. It's believed to be a pseudo-random function. But why is it a pseudo-random function? Why is it a secure pseudo-random function? We have no idea. We just believe that it is a pseudo-random function. That's our assumption. And there's no reduction to a non-interactive assumption. So you see, this is what I mean by, in some sense, a failure of cryptography, in that we were supposed to take this highly interactive game and build secure pseudo-random function from a non-interactive assumption. And yet, we can't do this in a way that's practical. So the only thing that's practical is basically to kind of have this ad hoc construction called AES and just assume that it's a secure pseudo-random function. So it's kind of an open problem. It's been open for a long time, basically. Is there a way to construct a pseudo-random function from a secure non-interactive assumption, like we do for RSA and for like we do for signatures, for key exchange, and have the results actually be as fast as AES? If we could do this, this would actually, it literally could change the world, because there would be no reason to use AES anymore. You might as well, if everybody believed this non-interactive assumption, you would be much better off using that primitive. Okay, so what's the current state of constructing pseudo-random functions from non-interactive assumptions? Well, so there's old results. So there are old results that actually show how to do it. So there's the famous GGM construction that show how to construct PRFs from non-interactive assumption. The only problem is it's a lot slower than AES, about 100 times slower than AES. So nobody will use that, unfortunately. Even though it's a beautiful construction, no one will use it. There are other beautiful constructions. For example, there's one that's really, really quite elegant. This is one that's due to Orr and Ringel back in '96. This one is based on the decision Diffie-Hellman problem. And let me just quickly walk you through this construction, because it will become relevant in just a minute. Basically, the key for this construction is, so there's a finite cyclic group of order P, prime order P. And the key is basically a vector of n plus 1 elements mod P, so in Z mod P. The input, the domain of the function is just 0, 1 to the n, so we have n bits as inputs. And the way you evaluate the function is literally you just compute this exponent here. So this is a subset product of the keys, right? So the x's, remember, are 0, 1. X's are just 0, 1. So this is a subset product of the keys, k0 to kn. You compute this exponent, and then you raise the whole thing to the power of, and then you do g to the power of that exponent. So essentially, evaluating it is relatively simple. It requires a multiplication of, say, 100 elements, and then one exponentiation. That's it. Yeah, so this is a wonderful, wonderful PRF. And in fact, you can prove that it's secure if the decision Diffie-Hellman assumption holds in the group G. I won't explain what that is. That is a nice non-interactive assumption. We all know and love this assumption. The problem is, again, this is a lot slower than AES. But I want you to remember this structure, because we'll come back to it in just a minute. And then Chris has this beautiful results, Baranjit, Pikert, and Rosen have this beautiful results on, I would say, also kind of taking this style construction and building it from lattices based on LWE. Also generalized synthesizers, other kind of constructions that are also able to give to construct based on LWE. This is faster than Noah Reingold, the original Noah Reingold. Chris, you say that this is about 10x slower than AES. I see. Yes, I want to prove. That's the whole point. I see. Is that right? Okay. Well, let's be generous. Let's say this is 10x slower than AES and reducible to LWE. Let's be generous. Yeah. But still, 10x is still slower than 1x. So again, everybody will use AES. They will not use this. Yeah. So you see that. So I hope I kind of am getting this. It's kind of a depressing situation that we're in. That we have these reams and reams of wonderful constructions that we have all over crypto, and yet the most fundamental primitive we want to build, PRF, we're stuck using something that's completely ad hoc. Yeah, it's really kind of a blemish in the whole theory of crypto that we have not been able to come up with a fast construction that's as secure as a non-interactive assumption. So we need help here. Yeah, we don't know how to do it, but maybe one of you guys will have a good idea. So why am I giving this talk? Well, the hope, and by the way, I should preempt this by saying this did not work, but nevertheless, let me tell you, the hope is that in fact, hard problems in group theory could actually help out. Yeah, so if there are group theorists in the audience, take out your favorite hard problem from computational group theory, and the claim is that if we can build pseudo-random functions from these hard problems, that will be phenomenal. That would be phenomenal, and actually there's a chance that they will be fast. So let me suggest one particular problem. I don't know if it's hard. I don't know if it's not hard. Maybe one of you guys will just, Daniel, maybe will just get up and say, no, this is never hard. I don't know. Let me just tell you what problem I want to look at, and you guys tell me what you think. So the problem is a classic problem. This is one of Max Denn's original problems, right? The conjugacy problem. Let me define it for you quickly. So we have an ambient group K. So yes, okay, some group could be infinite. I don't really care. It's going to be an ambient group that we're going to work with. All I need is a K has an efficient group operation. And in fact, I would want it to have a fast group operation. So not Burnside. Yeah, I want it to have a fast group operation because we want to be competitive with AES here. Okay, so now we're going to have. I'm going to use standard notation. I'm going to denote by G to the power of sigma. I'm going to denote the conjugation of G by sigma. G to the power of sigma. This is standard notation, which, as you'll see in a minute, is quite amusing with where we're headed. And now I'm going to have two sets, G and H. So G is going to be some subset of K. I'll explain what that is in just a minute. And H, I want it to be a subgroup of K, an actual subgroup. Both of these are going to be finite, but they're going to be large. There's going to be exponential in the security parameter. And the other requirement I want is you should think of G as sort of a conjugacy class. So I want G to be closed under conjugation by H. Okay, so G, think of it again as like a conjugacy class of K, but it could be even larger than that, yeah, because we're only conjugating by H. We're not conjugating by all of K. All right, so now we understand the setup. So let's look at the conjugacy problem. So problem number one would be the following question. I give you an element in G, and I choose an element in G, and I choose an element in H. And what I do is I give you G, and G conjugated by sigma. Okay, G and its conjugate. And your challenge is find me the conjugator. So find me a conjugator that maps G to H. Yes, so again, this is this is the search problem. Let me state the decision problem. The decision problem would be, this is written like crypto folks would like to write it, is basically says the following. If I give you two random elements in G, that looks the same as giving you a random element in G and its conjugate. So if this problem is hard, this is the search problem, you cannot find the conjugator from H to G. There's hope that the decision problem is also hard, namely that a G and a random conjugate of G would look like just two random elements in G as well. Okay, so this is kind of a version of the classic conjugacy problem. One of Max Denn's standard problems. This problem, like not the distribution version of this, but the worst case version of this decision problem is non-computable for infinite groups, right? So these are kind of hard problems generally in group theory. Yes, do folks know this? It's like for infinite groups, given a group presentation, conjugacy problem generally is undecidable. But here, of course, we're not looking at infinite groups. We're looking at finite groups. And I'm not looking at the worst case version of the decision problem. I'm looking at random instances of the decision problem. And the question is, are there groups for which this is hard? Yeah. Well, so there are groups for which this is easy. Let me give you just one example. If you allow me to use, just to make the example interesting, I'll use infinite groups for just a minute. For example, if G is the simple linear group mod over the rationals, and H is the simple linear group over the integers, if I give you an element, an n by n matrix, and its conjugation by an integer matrix, the question is, could you recover the conjugator? And it turns out the answer is yes. Yeah, there are actually algorithms that will recover a conjugator from, well, given two conjugates, it will find an integer conjugator between them. Yeah, so this problem is not always hard. But the question is, are there groups where it is hard? Yes? For entropy reasons, a lot smaller? No, you want it bigger, right? I mean, because then you want G to the sigma to be kind of indistinguishable from a uniform element. Not necessarily, right? I mean, H, the conjugation of little g by H is going to define some conjugacy class inside of big G. So I guess the bigger H is, yeah, I mean, I don't know that it matters what the relative size of H to G are. Oh, I see what you mean. For it to be useful. Oh, there could be. I see what you're saying. So it's not an issue of size. It could be, for example. Okay, so one thing which would make this trivial would be, is, for example, if little g to the power of h is all of g. Yeah, then this would not be. So those would be. So then this problem is trivially hard. So the distributions are equal. So it's not so much a matter of size. It's more of a matter of structure, right? You want little g to the power of h to be less than all of g. Yeah, that's it. Right, that's a good question. All right, so now that we have these problems, let me just tell you that, in fact, they immediately give us PRFs. So here's a PRF. Now, the thing that okay, so let me just go through it first of all. So the key is going to be an element of capital G, and then sigma 1 to sigma n are going to be elements of H. Okay, so that's going to be the key. The domain is going to be 0, 1 to the n, so these are bits. And this should look familiar to you. Yeah, what did I call this? I call this the Noor-Reingold generator, but it's not. This is using the same notation, but the symbols here mean completely different things. Yeah, this is not about exponentiation. This is all about conjugation. So what you do is you create this subset product, and then you conjugate G by that subset product. So really, if I expand this out for you, this really is what this PRF is. Okay? Yeah, so that's the PRF. And it turns out you can actually analyze the purity of this PRF. This PRF actually follows from a general paradigm of building pseudo-random functions called something called the augmented cascade paradigm. And there's a theorem that you can argue, that you can actually show that this construction is in fact a secure pseudo-random function if a certain conjugacy problem is hard. Okay, well, let me show you what. Does everybody absorb the construction? So you create, so given the input, the bit vector x, you create the subset product, and then you conjugate G by the subset product. That's it. Very, very simple. And you can see literally evaluating the PRF is just a matter of taking a couple of group operations. So if the group operation happens to be fast, this could actually be quite fast, and in fact it's parallelizable. So if you have to implement it in hardware, it's actually quite fast. And so there's a potential here for getting fast pseudo-random functions. So what is the assumption that we need here? I just wrote it up for you. It's a variant of, it's a harder assumption than the conjugate. It's a stronger assumption than the standard conjugation problem. The assumption is that it's kind of a Q-way variant of the conjugacy problem. The problem is you want to say that given G1 to GQ and one conjugator, taking all these G's and conjugating them by the same conjugator still looks uniform. That's the assumption. And if this assumption holds, then we know that this PRF is secure. Yes? So you get a fast PRF, assuming the group operation is fast. You get a fast PRF under this very concrete, non-interactive assumption. And my challenge to you is, well, maybe you can tell me that this never holds. Or maybe you can find groups for which this does hold. And if you could find groups for which this does hold, then we have potentially really fast PRFs under a non-interactive assumption. Okay, so I'm going to skip some of this. Oh yeah, I didn't say what. Thank you. I didn't say what Q is. Q is yeah. Q is actually, well, Q minus 1 is the number of queries that the adversary makes. So generally, Q will be polynomial, but you can already start. Fine, I'll make this. I'll make my last note. You can already start to see that there are interesting things you can do here. For example, if G happens to be a group, then you can see that given like 5 of these things, 5 of these pairs, you can start creating words of them. And from 5 pairs, you can create many, many more pairs. So in fact, you don't have to go all the way up to Q. You just have to go, you don't have to have Q of these. You just need to have enough of these so that random words in the generators, in the elements you were given, generate random elements in the group. Yeah, is that clear? You can, from a few samples, you can generate more samples. And so you don't actually need to have, Q doesn't actually have to be this big. A small Q, a small set of samples of this form would actually imply this assumption even for large. Right. Okay. So my challenge to you is so my points are this. To summarize this quick talk, my point was take out please look for hard problems in group theory. It's pretty clear that hard problems in group theory can give us fast PRFs. So take out your textbook or take out your favorite hard problem from group theory and let's try to build fast PRF from it. This really could have an impact in practice if we could make it faster than AES. So that's kind of the high level goal. And then I just outlined one particular approach. And the reason I say that it failed is because I couldn't find groups that satisfy the assumption that we needed. Then maybe you guys can. Right, so are there finite G and H like we needed that satisfy the conjugacy problems that we needed? And can we make the resulting PRF fast? And for extra bonus, that's, extra points, can we build other primitives from these conjugacy problems? Like, for example, can we build collision-resistant hash functions from conjugacy? Again, I don't know how to do it, but maybe that's possible. All right, so my point, actually, my meta point was, if you're going to use group theory to do things, don't think necessarily about using them for key exchange or for FHE. Those are fun things to build. But really where we need help is in building PRFs, because that's where the theory really has a hole. And it'd be nice to plug that hole using group theory. Great. Okay. So we're gonna don't clap because we're gonna tag team. Any questions on it? Yeah. Yeah, because it's basically just. Oh, no, it's gonna kill no wrangle. The question is, why is it gonna be faster than AES? You're just doing. Yeah, I mean, n typically a typical value of n is 128, like it is for AES. So all you're doing is just 256 multiplication. You want 256 multiplications to be faster than 10 rounds of AES. And by the way, 10 rounds of AES produces 16 bytes of output. 16 bytes. This thing would likely produce many more than 16 bytes of output. In fact, the comparison is even more in favor of it. So if the group operation is sufficiently fast, this could be much faster than AES. Yeah. This is the question of the day. Excellent question. I think it's a great question. So these conjugacy problems, generally, for infinite groups, they're undecidable. So in principle, there's no reason why they should be vulnerable to quantum attacks. So it's all a matter of choice of groups. If we choose the groups so that we can't break the conjugacy problem under a quantum attack, then yeah, it will be quantum resistant. So the short answer is yes, we would like it to be quantum resistant. Right. That's fine. Yeah, that's fine. True. Yeah, I agree. Definitely. I mean, there's no reason why they can't all have the same order. Yeah, absolutely. That's a good point. Yeah. Which one are you referring to? Yeah, I know what you mean. I got it. Yeah, I got it. So let me. So the actually, I'm glad you brought that up. So first of all, what you're describing is a pseudorandom generator, not a pseudorandom function. So it's a much weaker primitive. A pseudorandom function is a function. You can evaluate it. Here, let me go back to my definition. Where is here? Alice. Yeah, it's a function. Wow, wait. Like a block cipher. Yeah. A pseudo-random generator is not something that you can evaluate at a random point. Yeah. And in fact, to generate the Fourier coefficients of an elliptic curve, you do have to do it sequentially. So you don't have random access to the string. Say that again. So. Wait, then I can have random, but if I want to evaluate it like it. But that would be slow, wouldn't it? Now you don't. Now it's not that fast. Yeah. That's a problem. That's a problem. Yeah, so that by now you've killed performance. Now it's never going to be faster than AES. Generating primes, yeah. So that's a problem. So again, I would say a pseudorandom generator is a different problem. And in fact, when we talk about pseudorandom generators, we have things that are even orders of magnitude faster than AES. So now your competitor has become way faster. It's an easier primitive. Yeah. So we're interested in pseudorandom functions. Now you can go from a pseudorandom generator to a pseudorandom function, but that's a factor of 100 in performance. That's the problem. Yeah. Good. I'm glad you brought it up. That's a really good question. Cool. All right. So Craig, you're on. Absolutely. No. Conjugacy problem in abelian groups is not very. No, but yeah, and both of them are abelian, but they don't interact in an abelian. They're not commutative among themselves. Yeah. Yeah, that'd be fine. Actually, that'd be great. Yeah, if that's true. So they have some complicated operations among them, but themselves are abelian. Yeah. I think that'd be great. Absolutely. Yeah. If you have a concrete set. Say it again. Yeah, I don't see why they can't be abelian. But we need to have so the question is, we need a concrete proposal for how G and H would interact to make the conjugacy hard. But it's a great idea. Yeah. We should try it. The G's themselves. Well, you get a bunch of different G's from capital G. But is that gonna yeah? But is that gonna help you distinguish from random? So maybe that means G can't be a billion, but maybe H can be. Yeah, because for a billion, you can usually find relations. Given the G1 to Gn, you can find a relation on the G1 to Gn that maps to the identity. For a billion, that's not a hard problem. And then here, let's go back to, yeah, this is really good. This is a good discussion. Sorry, Craig. Yeah, this assumption is kind of the crux of it. So you want this problem to be hard. Now, suppose you could find, given G1 to GQ, suppose you can find a word on G1 to GQ that happens to multiply to 1. Then the conjugates would also multiply to 1. So at the very least, you want the word problem to be hard for capital G. So G, this means, yeah, so good, thanks for that. So this means G can't be a billion. But H could still be a billion. Yeah, I'm not clear why that can't be. But yeah, you want the group word problem to be hard for G. Yeah. So great. Yeah, I'm glad you like it. So please think about this. If you have suggestions, would be fantastic. All right. So now you're on, Craig. Sorry. Oh, yes.
Okay, so I'll talk about some open problems in FHE. Oh, yeah. Okay. So I want to say sort of the opposite of what Dan said, that you really should think about group theory in terms of FHE. I think that's and PRFs are great, but really we want to focus on FHE because that's also another hole in our understanding. So let me sort of review FHE for you. So basically the idea is that the typical setting is the setting where Alice wants to delegate her computation. Fully homomorphic encryption. So Alice has a bunch of data and she wants to put it up on the cloud, but she doesn't trust the cloud, right? Because they're all all these companies are compromised every week. So she wants to put her data on the cloud encrypted. But on the other hand, she wants to get the benefit of cloud computing. In particular, she wants to make queries to the cloud, some function f. And she wants to receive back basically the function f applied to her data, okay, but encrypted, in an encrypted form. So the question is sort of how is the server going to do this if it's encrypted and it doesn't have the decryption key? And the answer is fully homomorphic encryption. It's just an encryption scheme that allows this to happen. A system where operations on ciphertext induce operations on the underlying messages in a predictable, controlled way. Okay. So, since this is a mathematical audience, I thought I'd put a commutative diagram. So you could, I don't typically describe it this way, but the key property of homomorphic encryption is that it doesn't matter which order you perform the computational operations and the decryption operation. So if you start from a bunch of ciphertexts and you just, first of all, just decrypt them and get a bunch of messages, and apply the function, you get something. Or if, on the other hand, you do operations on the ciphertexts homomorphically, and then at that point decrypt the final result, the result should be the same either way. Right? So the computation, in some sense, commutes with the decryption operation. Okay? And so just so you understand what I'm talking about when I say computation, basically computations can be broken down into Boolean circuits. So we can just view function as a circuit with addition and multiplication gates. which essentially compute polynomials. Yeah. So it's just yeah, I put more detail in here than I wanted to get into, but a circuit is a directed acyclic graph. You take some inputs and it feeds through this graph, and it gets operated on at the gates by addition and multiplication gates, and finally you have some output, which is a polynomial, multivariate polynomial. Right? Okay, so there are lots of open problems in FHE. Probably the biggest one is to make it really efficient. I mean, we're still trying to do that for PRFs, so I guess that's always an open problem in cryptography. And there are all sorts of other sort of, I guess I would call them obscure problems that are of interest only to us cryptographers. So rather than going into those, I want to go into a couple problems that are more appropriate for the more mathematical audience. And basically, I'm just sort of stealing a couple of people's talk a little bit. So I want to talk about Koji Nuita's scheme a little bit more to see if we can sort of have some sort of resolution on that, whether it can possibly work. And also, I want to talk about FHE for quantum computation. So we have FHE schemes for classical computation, which can be expressed as Boolean circuits, but quantum computation can't be efficiently expressed in that way. Okay, the gates are a little more complicated than just addition and multiplication. Okay, so just at a very high level, if we try to think, we want to create a new FHE scheme, sort of the obvious thing to try to do is to use ring homomorphisms. So the idea is just that the ciphertexts live in some ring R sub C, the messages live in some ring R sub M, and basically decryption is just a ring homomorphism. Okay? So then if you do addition or multiplication of ciphertexts, it just induces addition or multiplication of the underlying messages. Really simple. So one thing to notice is that encryptions of 0 form an ideal in this ring. So what we want encryptions of 0 to be indistinguishable from encryptions of other things. So for it to be secure, it has to be the case that the ideal membership problem is hard in this ring. Okay, so let me just give you an example of this from the 90s called Polycracker by Fellows and Koblitz. Basically, the idea is that the secret key is just some vector S, and the public key is just a bunch of polynomials that evaluate to 0 at S. I'm not going to go into too much detail about how these polynomials are constructed, but so this is a little hand wavy, but they just evaluate to 0 at the secret key. Now again, this is fuzzy, but encryption is some process of taking the public key and first of all creating a random encryption of 0 by adding and multiplying together the polynomials from the public key to get another polynomial that evaluates to 0 at S. Okay, and then to that you just add your message. Okay, and decryption is simple. You just evaluate the final polynomial, which is the ciphertext at S, and it should just be the message that you encrypted. Okay, homomorphic operations. I guess I don't, if there's a good story. Oh, well, I guess they had, I don't know, they were talking about polynomials and they thought it was funny, Polycracker, I don't know. I have no idea. Okay. So, homomorphic operations are pretty easy to see. If you just add the underlying ciphertext, obviously it adds the evaluations, and same for multiplication. Okay. And you could break this scheme if you could detect whether C has a common root, defines the ciphertext C has a common root with the Fs, because this is to detect encryptions of 0. We don't want to be able to distinguish encryptions of 0 from general encryptions. Okay. So, but this scheme never really worked, and the reason is basically that these are basically huge multivariate polynomials, and when you add and multiply them together, you're going to have, an enormous polynomial, right? You can try to make it the case that somehow the multivariate polynomials are restricted to some smaller set of monomials. But in that case, it's actually pretty easy to break. Basically, you just have a, encryptions, you can just sort of view it as a linear system over these different monomials. And encryptions of 0 will exist in some subspace of the total space of ciphertext over that basis of monomials. Okay, it's very easy to detect just using linear algebra. Okay, so a little bit more specifically, if you have a target ciphertext C and you wanted to distinguish whether to encrypt 0 or not, you first of all generate a lot of encryptions of C on your own, which eventually will probably generate the whole space of encryptions of 0, and then you just determine whether your target ciphertext is in that space. Okay? Yeah, so otherwise, if there's no way to restrict a sort of a small set of monomials, then the ciphertext size gets kind of completely out of hand, and it's not an efficient scheme. Okay, so here's another approach using ring homomorphisms and something that stays compact, but this isn't secure either. So basically, the idea is that ciphertext will be matrices. The secret key will be a vector, an eigenvector, in fact, of all the ciphertexts. And the message encrypted will be the particular eigenvalue. Okay, modulo Q. So homomorphisms, you add the ciphertext, and that adds the eigenvalues, and same for multiplication. Okay, but again, encryptions of 0 are going to live in some subspace. So it's easy to distinguish encryptions of 0. So there is actually a scheme, Dan will say a little bit more about this, but there is actually a scheme that looks like this. It's not what we say semantically secure, because you can distinguish whether 0 is encrypted or some other value. But if you just encrypt random values and you only use the scheme sort of one time, then in that case, I'll leave it to you. So, it's not completely useless, but it's pretty difficult to use. But it turns out that we have an FHE scheme that looks basically exactly like this, except we patch it just a little bit to prevent the linear algebra attack. What we do is we just sprinkle on a little noise to these equations. And in particular, we just have ciphertext satisfy this equation, that the ciphertext times the secret key vector is not exactly some scalar multiple of the secret key vector, but that plus some noise. Okay. And basically the whole idea of LWE is that you just sprinkle on a little noise to mess up linear algebra attacks. And so doing this actually works. You can get an FHE scheme that looks like this. And I'll just go over it briefly. This is just so you can kind of see how we do FHE now, and then then I'll sort of describe what the problems with this approach are and why we want other approaches using group theory. Okay, so if you want to do addition and multiplication of ciphertexts, so addition, it adds the eigenvalues together, and it also adds the noises together. So in Jeff's terminology, the resulting error is pretty short, if the original errors were short. In multiplication, it's kind of more complicated. So you have all sorts of cross-product fun going on, but what you end up with at the end is something that you want, namely the product of the eigenvalues with your secret key. That part has the correct form, but then your new noise vector has kind of a strange form. It's the second message times the first error, and the first plus the first ciphertext times the second error. Okay. So we would like to say that that new noise is small. It's pretty short. And you can do this. So basically what we do is, like, if you just restrict all the messages, all the mu's here, to be 0 or 1 values, since we're interested in evaluating Boolean circuits, then having mu2 be 0 or 1 there is not going to contribute much to the noise if the original E1 was small. The tough part is the C1 times E2 part. And basically there's a procedure. So C isn't going to originally be kind of a small matrix, but before we do an operation, there's kind of a way to make it small so that it has entries in 0, 1. And once we do that, and it's multiplied by E2, then it'll be a 0, 1 vector times E2, which will still be pretty short. So I'm not going to go too much into that, but this is kind of how FHE schemes currently work. We do homomorphic operations through addition and multiplication. This increases the noise, and we constantly have to worry about if the noise is becoming so big that these values wrap modulo q, and we can't decrypt correctly anymore. So that limits the number of operations that we can do, and additionally it slows things down because we have to set the underlying modulus q to be big enough to accommodate the growth of this noise, so our parameters become more and more huge. And because q becomes larger, we also have to make the lattice dimensions larger to ensure that the underlying lattice problems are still hard. So this is the problem with current FHE schemes. So now I want to kind of go to FHE without noise. I would love to see whether this is possible or not. So I just want to kind of remind us of Koji's scheme. My description looks different from his. This might be a special case of his scheme. I don't know. We can talk about it. But this is kind of how I view his scheme. And I'll just review it. Okay, so, all right, good. Oops. So basically what I want are this. So this is my group theory question to you. So I would like perfect group pairs with certain cryptographic properties. So what I mean by perfect group pair is a pair of groups G and H, where H is a normal subgroup of G, non-trivial. And G and H are both perfect groups. In other words, they're equal to their own commutators. Okay? So I want that. And I want also, I need some basic things like, that group operations are efficient in some sense, in that it's possible to, from a bunch of generators of G or a bunch of generators of H, it's possible to kind of randomize them and maybe reduce the number of them a little bit. So there's some basic group operation stuff, but the important thing is that in terms of security, what I would like is that given G and H in terms of their generators, you have a bunch of generators which generate G or H. I want it to be hard to distinguish which is the case. Okay, so I need a perfect group pair. H is a normal subgroup of G. G and H are both perfect, and yet it's still hard to distinguish G and H given a bunch of generators. Okay, so if you have that, then Koji has a scheme which looks basically like this. So basically, an encryption of 0 is a bunch of generators of G, an encryption of 1, a bunch of generators of H. And then you have some secret key, which, I don't know exactly what the form of that will be, that allows you to distinguish G from H. I won't talk about that part. The way you encrypt is you just take the generators. In the public key, you have, generators of G and H. So you take whichever group, depending on which bit you want to encrypt, you take those generators, you randomize them a little bit, and that's your ciphertext. I create new generators of the same group. Yeah, just create random words, and let's hope the group is such that if you do this just in a perfectly uniform way, that the generators still generate the whole group, and the number of generators doesn't get out of hand. You just have to do this, a few times to get a few generators. Okay. Yeah. Yes. Okay. So so all I need to do is an AND and an OR gate. So we're not going to do addition and multiplication gates. All I need is AND and OR. You can push all the knots down to the bottom of, if you have a circuit with knots in it, you can push them all down to the bottom of the circuit using De Morgan's law, and that basically deals with them. So I just need AND and OR. So to do AND, so I have two different groups represented by their generators, K1 and K2. I don't know what they are. Okay. To compute the AND, I just take the union of the generators. Okay. So if I take the union of the generators, the group that I get is the bigger of the two original groups, right? And you can see how that corresponds to a AND operation, right? Because if either of the two groups is G, then I'll get back G, which is a 0. So if either two input bits are 0, the output bit is 0, and otherwise it's 1. Okay? So that's an AND gate. Does that make sense? OR gate, I'm going to use the commutator. Okay? So commutator of G and G is G, and H is H, and the commutator of G and H will be H, because H is normal in G and perfect. Okay, so this does kind of the opposite of what the union does. It gives the smaller of the two groups, like taking the commutator. So it's an OR operation. H is perfect, which means.
But if I take all commutators of the pairs of the generators, then do you generate the group?
Yeah, the group generated by the commutators.
All commutators, not just commutators of generators.
Yeah, I don't just take all the commutators. I take the group generated by. So I generate all a bunch of commutators, and then I kind of take the group generated by that, using my randomization process, and then hopefully the properties will be such that that's the proper group. Okay, so the question is just, I think this is a special case of Koji's scheme, so there might be some more flexibility in his. So the question is just whether these perfect group pairs exist with the additional cryptographic property needed for security. You can easily construct perfect group pairs as direct products, but you're not going to get much security there because you just sort of have two positions. G is non-trivial in both positions, and H is non-trivial in one, so pretty easy to distinguish. Yeah, so that's just a problem. So you can come up with examples that are easy to break. So, for example, you can make G elements like this, where the H elements are just diagonal in the upper left corner. That's the only difference. But it's in R. The R's are just random matrices to conjugate by. But these are pretty easy to distinguish because basically the G's live in a higher dimensional space than the H's do. Essentially what Koji said is that it's not just a matter of group operations. You also have this additive aspect, which you can exploit if these are represented as matrices. and you can just detect that G just lives in a higher dimensional space than H. Well, I think that's true. So that's kind of my question. So what is there that can be done here? It seems like if you just have sort of naked matrix group representations, then it does seem like you can use the additive structure and linear algebra to distinguish between the groups. But so I don't know much about the Tizzi transformations, how much they obscure the underlying, if there is an underlying matrix group, how much it's obscured by these transformations. So, any thoughts? So I don't know. So I'm a little pessimistic on at least my version of this scheme, where you have these. I just wonder if there's some trivial way, to break it. If assuming G and H have all these special properties, there aren't that many perfect groups. Basically the Lie, sort of Lie type groups, and well, they're simple groups, but cryptographically useful ones seem to be maybe Lie type groups. Yeah, basically, if you just, I guess it's sort of a, how the group is represented or presented. So, if it was a direct product and it was just represented in this sort of naked way as two components, where, H is kind of trivial in the second component and G is not, then it would be easy to distinguish between those two cases. Oh, I don't know. So nothing I've looked at works, but and another kind of problem with this, I think, is that typically in these schemes, at least if it's sort of some matrix group scheme, the decryption operation is just a linear function. So kind of the projection that Koji was talking about, this projection function, if it's just linear, if decryption is just linear, that's not good, because we want decryption to be a non-learnable function, right? It should be the case that, so basically an attacker can create ciphertext on his own and kind of see how the decryption operation works. And if it's just a matter of this linear function, then it can't be secure. Decryption has to be sort of a high degree function to be non-learnable. Yeah, if it's a public key system, you just generate ciphertext on your own. So you kind of generate your test set by yourself, right? You just generate a test set of a bunch of messages and ciphertext on your own. And if decryption is just a linear operation, then you can learn it from this test set. Well, I kind of left it open because I don't know how. These groups might be represented in a crazy way that requires some complicated decryption process, which is kind of what I want. If it were really simple like these matrices, then that's where the problems arise. So yeah, you want a trapdoor, but yeah, you also want that trapdoor to be maybe a little bit complicated. Okay. So otherwise, I was going to give sort of a prelude to Stacy's talk. Well, that's what I'm asking. I don't know. I kind of suspect that there might be for all these very strict requirements that I have. Yeah. I mean, just something in representation theory or group theory that says that, if, H is normal in G and then they're perfect, I don't know. Then there's just something you can do to tear apart the scheme.